Welcome back to episode 41 of the Quantum Science Seminar, which today is all going to be about two-electron atoms and quantum gases. As usual, we would like to have your questions. Please send us your questions to quantumscienceseminar@gmail.com or use the YouTube live chat at the right or at the bottom of the screen. Please also note that there's a 30-second time delay between what we do here and between what you see on YouTube as live. And with that, I'd like to hand over to our special guest, Simon Völling, who will be introducing our speaker today.
Yeah, thank you, Sebastian. And also from my side, thanks to everyone for tuning in today at this unusual hour for the seminar. But it's worth it. We are especially delighted today to welcome Professor Yoshiro Takahashi, who's joining us online from Japan. So Professor Takahashi obtained his PhD from Kyoto University in 1992, where he worked on laser spectroscopy, originally on impurity ions in solids. And after that, he stayed in Kyoto immediately as an assistant professor to apply his laser spectroscopy experience and techniques to neutral atoms for the first time embedded in liquid helium at that point. Then very soon he started branching out into what was still quite novel field in cold atoms, laser cooling in cold atoms in the mid-90s, and working from the start with alkali atoms, but particularly also with ytterbium, which we will hear about today. So basically we can say that Yoshiro was already working with alkaline earth-like atoms before they were cool. So and you can understand that basically both figuratively as well as quite literally, because when he decided to start this effort, ytterbium gases were far away from quantum degeneracy, and years of hard work were needed to find all the suitable techniques for efficiently cooling ytterbium and solving all the problems and eventually reaching degeneracy in 2007, I believe. So basically for all of those and us that work with ytterbium, it's really Yoshiro's work that is the lighthouse and the benchmark that we always look at first. So since those first degenerate quantum gases, much like the field itself, Yoshiro and his group has contributed to a huge range of topics in ultra-cold gases and beyond, using both ytterbium and also alkali atoms with molecular physics topics, mixtures of different isotopes, different mixtures of different atoms, as well as optical lattices and all other kinds of aspects of cold atoms. Basically everything the field has to offer, he has been contributing. So today he will tell us about the newest developments on realizing and observing quantum magnetism, and in particular with cold SUN Fermi-Hubbard model atoms using ytterbium. So without further ado, thank you, Yoshiro, and yeah, the stage is yours.
Okay, can you hear me? Okay, thank you very much for introduction, and also I would like to thank the organizers for kind invitation to this nice quantum science seminar. The title of my talk is Quantum Magnetism of Cold Atom SUN Fermi-Hubbard Model. Okay. Now, sorry, it's freezed. So I tentatively start again. I think it works. Okay. This is a tight outline of my talk today. First, I will make a brief introduction of quantum simulation of Fermi-Hubbard model with special emphasis on quantum magnetism of Fermi-Hubbard model and SUN Fermi-Hubbard model and Pomeranchuk cooling. And next, I will describe in detail our recent experiment on quantum magnetism of SUN Fermi-Hubbard model. And I will report on the observation of the antiferromagnetic spin correlation of SUN fermions. And also I will talk about our recent experiment on dissipative Fermi-Hubbard model and SU4 singlet state in a Plaquette lattice. Okay, first I will talk about the quantum simulation of Fermi-Hubbard model. the Fermi-Hubbard model is described by this Hubbard Hamiltonian. Here, the first term describes the hopping between adjacent lattice sites, and this term is characterized by the tunneling amplitude T. And second term describes the on-site interaction when the two particles occupy the same lattice site. And this term is characterized by the on-site interaction energy U here. And this Hubbard model is very important in condensed matter physics because it describes the strongly correlated electron system. And this Hubbard model is a minimum model to describe the unconventional superconductivity and novel quantum magnetism. Yeah, this Hubbard model takes a very simple form, but it is very difficult to solve by numerical simulation with classical computers. Various powerful numerical methods like these were developed, but applicability of these methods are limited to specific cases. So we need a quantum simulator of Fermi-Hubbard model. Okay, so in this respect, a system of ultracold atoms in optical lattice is believed to be an ideal quantum simulator because it is quite clean system with no lattice defects or impurities, and it has a high controllability of a system parameters of a hopping T and on-site interaction U. And we can take various lattice geometries of the optical lattice corresponding to real materials and so on. And we can prepare the ultracold Fermi gas with a temperature much below the Fermi temperature with the evaporative cooling method in a harmonic trap. By loading it to optical lattice, we can successfully implement the Fermi-Hubbard model using ultracold atoms in optical lattice. And one of the goals of such a quantum simulation of the Fermi-Hubbard model using cold atoms is to get deeper insight on the physics of strongly correlated electron system, such as the Lattice-Triplet. Here, I show the phase diagram or schematic phase diagram of the Lattice-Triplet here. Even after 30 years of its discovery, the phase diagram is not yet well understood. Okay, so state-of-the-art quantum simulation research of a Fermi-Hubbard model using cold atoms now reveal the quantum magnetism of the Fermi-Hubbard system. And experiments are done by using the two-component fermions of lithium-6 or potassium-40. And ETH group was the first to study the short-range magnetism of a Fermi-Hubbard model with the technique of Singlet-Triplet oscillation. This STO technique is described in detail in my talk later. And the Rice group was the first to observe the spin correlation in a 3D optical lattice by a technique of black light scattering method. Okay, and more recent study uses a powerful technique of a quantum gas microscope like this. And with this technique, one can detect and manipulate single atoms with single site resolution. And using this quantum gas microscope technique, MIT group, Harvard group, and Max Planck group, and also Princeton group successfully observed the spin correlation in 1D or 2D optical lattices. In particular, the Harvard group successfully create and observe the antiferromagnet of the in a 2D Fermi-Hubbard model. Okay, it's really nice. And more recent experiment studied the doping behavior of the Fermi-Hubbard model like this, and also the bilayer Fermi-Hubbard model by developing a new technique like this. Okay, all of these works, great achievement in the study of a Fermi-Hubbard model, and yeah, it's really nice. Different from these alkaline atoms Fermi-Hubbard system, if we are working with the two-electron atoms such as strontium or ytterbium with a nuclear spin I, then we can study the another exotic Fermi-Hubbard model with enlarged spin symmetry of SUN by exploiting the nuclear spin degrees of freedom here, which are decoupled from the electron angular momentum in these electronic states of singlet 0, ground state singlet 0, and metastable state of a triplet P0. And this is the SUN Hubbard model. Now, here, the on-site interaction U is independent of the nuclear spin component, pairs of a nuclear spin component. This assures the SUN symmetry of this system. Okay, and more explicitly, we define the nuclear spin permutation operators like this, and these operators satisfy the SUN algebra like this, and also SUN symmetry like this. Okay, and in the large U limit of the SUN Hubbard model become the SUN Heisenberg model like this. Here, the characteristic energy is the exchange energy given like this. And here we note that the theory of SUN Fermi-Hubbard model was discussed in these pioneering literatures. Okay, and SUN Heisenberg model predicts novel quantum magnetic phases of this system. Okay, in the case of SU2 loaded into square lattice at half filling, this antiferromagnet is predicted theoretically and actually observed experimentally. And in the case of SUN loaded into square lattice with 1/n filling, these exotic quantum magnetic phases are predicted. Okay. In the case of SU3, stripe line ordered phases predicted, and in the case of SU4, nail ordering of the dimers predicted, and in the case of SU5, exotic quantum phases like this is predicted. Okay, and in addition, upon doping, the D-wave superconductivity or superfluidity is predicted in the case of SU2. And for the case of SUN, there is almost no discussion about the doping behavior of these quantum magnetic phases. And there is some related works in the case of SU3 near the half filling by these authors. Okay, and in addition, introducing the spin imbalance provides the interesting possibility for the quantum phases of these states. And yeah, so far there were almost no discussion about the spin in behavior of spin imbalance in this state, but quite recently, the related works reported about the triangular lattice loaded with SU3 fermions under magnetic fields like this. Yeah, so this is interesting new direction of research of the Fermi-Hubbard model. Okay, here I would also like to mention advantages of working with SUN fermions in optical lattice. That is Pomeranchuk cooling of an atomic gas, named after the Russian theorists of Pomeranchuk. This Pomeranchuk cooling played an important role in the realization of the superfluid helium-3 historically. And now this Pomeranchuk cooling works very efficiently for our case. And owing to this Pomeranchuk cooling, we can realize a colder temperature for SUN system than for SU2 system. Okay, let me briefly explain this mechanism of Pomeranchuk cooling. And this can be understood by considering the entropy versus temperature diagram. Okay, and this line corresponds to the case of ideal Fermi gas in a harmonic trap before loading to the optical lattice. Yeah, okay, and after loading to the optical lattice, we have entropy versus temperature diagram, something like this. Here, we have characteristic value of the entropy of log 2 in the case of SU2. This entropy of log 2 corresponds to the spin degrees of freedom for each atom localized in optical lattice in a Mott insulator state. Okay, and in the case of SU6 in optical lattice, we have this curve. And here, the characteristic value of entropy is now log 6, corresponding to the spin degrees of freedom for each atom localized in optical lattice in the Mott insulator state. So, okay, suppose we have temperature of the atoms before loading to the lattice in a harmonic trap here, then the entropy takes this value. Then after loading, adiabatic loading to the optical lattice, we obtained this temperature for in the case of SU2. And in the case of SU6, we obtained this temperature after adiabatic loading. So this temperature is lower than the temperature obtained in SU2 case. So this is a Pomeranchuk cooling effect. Okay, and actually this Pomeranchuk cooling effect was observed in our previous experiment like this. And here, starting from the same initial temperature, then we obtain the lower temperature in the case of SU6 than in SU2 case. Yeah, and at this time, the temperature is a little bit higher, so the realized entropy is higher than this characteristic value of log 6. So the Pomeranchuk cooling works only for charge degrees of freedom instead of the spin degrees of freedom. In other words, Mott plateau is more easily formed in the case of SU6 than in SU2. Okay, and now we can prepare the colder samples in a harmonic trap. Then we can achieve a lower entropy. Then we can reach the quantum magnetic regime here. And so then the Pomeranchuk cooling works also for spin degrees of freedom. Yeah. So yeah, this is what we expect in the experiment. Okay. So this is the part of the introduction. So I think I can accept some question here.
Okay, well, thank you very much, Yoshiro, for the nice talk so far and the interesting introduction to this this really interesting field. So we have a few questions so far. So the first one is, does the sort of SUN physics that you're able to explore in your laboratory, does that also occur, for example, in some systems in solid state physics, or is this sort of really something that's unique to cold atoms?
Hmm. You mean SUN system is yes. Yeah, some solid state materials have approximate SUN symmetry. Yeah, but in a cold atom system, the SUN symmetry is almost perfect. Yeah. So this is because of the interatomic interaction is independent of the nuclear spin. So with sufficiently high level, the SUN symmetry holds in the case of the two-electron atoms. Yeah. So this is different from the solid state case.
Okay. Yeah, no, it's a really interesting system. And so one question as well is, what happens then as you keep sort of increasing N? So you sort of showed here that as you increase N, that you can get sort of more and more exotic phases. At the same time, we might expect, you know, as you have essentially more and more possible spin components, that the particles behave more and more as if they were distinguishable, almost classical particles. Could you say some more about sort of what you expect to happen sort of as you continue to increase in sort of with this combination of maybe the phases becoming more exotic, but the particles seeming more distinguishable?
Yes, there are detailed theoretical works about the quantum phases, about SUN system as a function of the filling and the number of spin components. Yeah. So in general, with increasing the number of spin components, quantum fluctuation becomes important. So exotic quantum phases expected. Yeah, but in a different context, if we increase the number of spin components, then it behaves like bosons. Yeah. So, but this is not the regime of a strongly correlated regime, I think. So, in a strongly correlated regime described by Fermi-Hubbard model, can host exotic quantum phases if we increase the number of spin components.
Okay.
Okay.
That's very interesting. So we have two questions sort of briefly then on Pomeranchuk cooling. So one question from Sandra Burb, who asks, are there limitations in Pomeranchuk cooling if N becomes even larger? So as you keep increasing the number of spins you have in your SUN system, are there limitations to how well this keeps working?
limitations with the increasing number of n. I don't think but in principle, by increasing the number of spin component, we expect a much larger Pomeranchuk cooling effect. But the total number of atoms is also limited in a cold atom experiment. So the number of the atoms per each spin component is reduced in real experiments. So but of course, if we increase the number of total atom number, then such a problem is not serious. So sorry, in principle, there's no. I don't think that there's fundamental limitation.
Okay. And just one final question, if that's okay at this point. So with Pomeranchuk cooling, it allows you clearly to reach lower temperatures as you increase the number of components. Could you say something about what happens to the critical temperatures of the corresponding phases as you increase the number of the number of spin components? So you're lowering the temperature of your system. Do the critical temperatures of the phases stay similar, or do they also change?
Yes, that's a very important question. So this is the quantum phases at zero temperature. So we don't know accurately about the critical temperature for these magnetic phases. So but by as I said, by doping or by introducing spin imbalance, various quantum phases expected. We think that some of the interesting quantum phases have reasonably high critical temperature, even with a larger number of spin component. So in principle, that quantum fluctuation becomes large for large n systems, so the critical temperature is expected to be low. Yeah, but I think there are several types of interesting quantum phases with a reasonably high critical temperature.
So thank you for that, Yoshiro. We'll save the rest of the questions to the end of the talk. Looking forward to the second half of the talk.
Okay, yeah. So I now switch to the second part of my talk. Okay. I will describe in detail our experiment on quantum magnetism of SUN Fermi-Hubbard model. And in our experiment, we used the ytterbium 173, which has a nuclear spin 5 Hertz and scattering length of this value. And this scattering length is independent of the nuclear spin pairs. So this assured the SUN symmetry of this system. And in our experiment, first we prepare the ultracold Fermi gas in a harmonic trap, and then load it into optical lattice. Okay, and here we can control the spin degrees of freedom with optical pumping, and we can confirm the spin distribution with the optical Stern-Gerlach imaging technique like this. Okay. And the first step of SUN quantum magnetism study is measuring the nearest neighbor spin correlation. And for this purpose, we utilize the STO, Singlet-Triplet oscillation method. And This method was first developed for bosons of rubidium-87 by Max Planck group, and later applied to the fermions of potassium-40 by Etihar group. And now we extend this method to SUN fermions of ytterbium-173. So let me briefly explain this method. Suppose we have some spin correlation between the neighboring lattice site here. To detect this spin correlation, first we freeze the intersite hopping by increase the optical lattice depth. And then we apply a spin-dependent potential gradient like this to induce the singlet-triplet oscillation. By introducing this spin-dependent potential gradient, we can introduce extra phase factor in the wave function here. So after some STO time, the initially prepared spin singlet state is transformed to a spin triplet state. And initially prepared spin triplet state is transformed to a spin singlet state. That's why this method is called singlet-triplet oscillation. And after the STO time, we merge these two sites into a single site. And if the singlet state is formed, then these two atoms are converted to the molecules by the application of the photo-association laser beam. And the created molecules eventually escape from the trap. And in the case of the spin triplet state is formed after the STO time, then these two atoms are not converted to the molecule and no atom loss. So in this way, we could detect the spin correlation as the atom loss behavior. Okay, and with this STO method, we can measure both of the spin singlet pairs and also spin triplet pairs. And from this measurement, we can deduce the important quantity to characterize the spin correlation, such as a normalized STO amplitude here, and also a singlet triplet imbalance here, defined here. Okay, and this is the typical STO signal of SU6 fermion loaded into a 1D chain with these Hubbard parameters. So this is a case of the strong link or intra-chain. We can clearly see the singlet-triplet oscillation signal like this. On the other hand, in the case of a weak link or inter-chain, we didn't observe a clear oscillation signal. And this is reasonable because the corresponding hopping between the interchain is very small. So corresponding exchange energy is very small. So we don't expect the formation of the spin correlation along this line. Okay, and if you see this signal, the STO signal is not a simple cosine function. And in fact, this is well fitted with this fitting function, which includes three frequency component, omega, 2 omega, and 3 omega with equal weight. And this is expected for our SU6 fermions because there are many pairs which have different STO frequency of omega and 2 omega and 3 omega. So yeah, this fitting function is reasonable, and from this fitting we can deduce the normalized STO amplitude like this, and also STO imbalance like this. Okay, and now we show the results of the systematic measurement of spin correlation for various initial entropy per particle. Yeah, this is a result. Here I plot the singlet-triplet imbalance as a function of the initial entropy per particle here. Okay, and green squares represent the case of SU6 fermion loaded in a 1D lattice. Okay, and blue triangles represent the case of the SU2 fermions loaded in a 1D lattice as a reference. Okay, and from the comparison of these results, we can say that we have a huge enhancement of the spin correlation with increasing number of spin component n from 2 to 6. And this is the nothing but the manifestation of the Pomeranchuk cooling for quantum magnetism. Okay, and red circles represent the case of SU6 fermions loaded in a 3D optical lattice. So from the comparison of these two results, we can say that we have an enhancement of the spin correlation for lower dimensional system. And this can be understood by the fact that for lower dimensional system, there are weak links like this, and we have a entropy redistribution in the weak links, and so weak links can carry the entropy, and but in the case of a 3D optical lattice, there is no such weak links. So yeah, so we expect enhancement of spin correlation for lower dimension due to the entropy redistribution in weak links. And this behavior is similar to the previous results obtained for SU2 system in a ETH group. Okay, and in addition to the singlet-triplet imbalance, we also plot the normalized STO amplitude as a function of the initial entropy per particle. And here you can see a similar behavior for these two quantities. And now these experimental data are compared with the theoretical calculation. Okay, and the SUN theory calculation was done by our collaborators of SUN theory team led by Caden Hazard of Rice University. They used the exact diagonalization method in the case of 1D lattice. And in the case of 3D, they used the determinantal quantum Monte Carlo with this geometry. And solid lines and dashed lines are results of the numerical calculation. Here you can see that the reasonable agreement between experiment and theoretical calculation. Yeah, this is impressive because the numerical calculation, the fitting does not, there's no fitting parameter here. So this is, we believe this is impressive. And yeah, and also I would like to point out the following fact that at the lower temperature regime of the SU6 fermion in a 3D optical lattice here, there are no available theoretical calculation. So at these regions, quantum simulation manifests its usefulness. Yeah. Okay, and from the theory experiment comparison, we can extract the temperature of the atoms of SU6 case in a 1D lattice. Here we plot the temperature of the atoms in optical lattice divided by hopping T as a function of the STO imbalance, normalized STO amplitude, initial entropy of the system, like this. And the calculations were done for various system sizes, like this. And green data point represent the result of the finite size scaling, like this. And experimental values here for the STO imbalance, and for STO amplitude here, and lowest entropy of the experiment correspond here. So from this theory experiment comparison, we can evaluate the temperature of the atoms here, like this. Yeah, and here you can see that the temperature estimated from the entropy is lower than the, this temperature. So this indicates the existence of some heating effect in a real experiment. Okay, and from the STO imbalance data, we can deduce the temperature of the atoms like this. And temperature is about 10% of the hopping T. So this is really cold. And this first error corresponds to the error of the calculation, and the second error corresponds to the experimental error. And we can evaluate the temperature similarly for the case of the SU2 atoms loaded in a 1D lattice, and the temperature of the atoms is almost equal to the hopping T. So we obtained 10 times reduction of the temperature by working with the SU6 fermions compared with the SU2 fermions. And this is a result of the Pomeranchuk cooling. So it works so efficiently in this case. And in addition, our temperature is compared with the lowest temperature ever reported for cold atom Fermi-Hubbard model, Fermi-Hubbard system, obtained by Hubbard group with this for the 2D lattice of the SU2 case. So this temperature is even lower than this temperature. So we can say that we achieved the lowest temperature of cold atom Fermi-Hubbard model. Yeah, it's good. And as an outlook, we expect to obtain further lower temperature by employing a spatial entropy redistribution technique, for example. Okay, and I would like to also mention the measurement of the dependence of the spin correlation on continuous lattice deformation. Yeah, such as the 1D to 2D, and also a 2D to 3D, like this. And this is a result of such a measurement. And here correspond to the 2D, and here correspond to 1D. And here correspond to the 3D case, and this correspond to the 2D case. So again, we observe the continuous enhancement of the spin correlation for lower dimensional system, which is again consistent with the results for SU2 system obtained by Etihad group. Okay, and now I switch to topic of quantum magnetism in an open dissipative Fermi-Hubbard system, which was discussed in recent theoretical paper by Dr. Nakagawa and others. Here we consider the simplest case of a two-site Fermi-Hubbard model, which is described by Heisenberg model with this exchange energy. And this is a case of the no dissipation. And if we introduce the two-body dissipation characterized by gamma 2b, then the system can be described by this effective Hamiltonian like this. And here the exchange energy is modified by the presence of the dissipation, and there appears a new term describes the dissipation of this system. And because the two-body dissipation is predominantly induced for the spin singlet pairs and no dissipation for spin triplet pair, so we can expect the sign reversal of the spin correlation from the initially prepared antiferromagnetic one to ferromagnetic one. Okay, and the behavior of the atom loss related with this situation was already reported in this theory paper and also experiment. And in our experiment, we directly probe the sign reversal of this spin correlation by STO technique. An experiment was done for ytterbium-1 with the ytterbium-173 loaded into a dimerized lattice like this, and two-body dissipation was introduced with the photoassociation process at this resonance. And this is the observed STO signal in the absence of dissipation, which indicates the formation of antiferromagnetic spin correlation. Then after the application of the dissipation, we observe this signal, which is we clearly observe the sign reversal of the STO signal, which indicates the formation of the ferromagnetic spin correlation by dissipation. And this is the time evolution of the spin correlation during the application of the dissipation. Yeah, we clearly see the transition from the spin antiferromagnetic spin correlation to ferromagnetic one. And we repeat this measurement for 3 different initial conditions. And for all cases, we observe the transition from antiferromagnetic to ferromagnetic spin correlation. And I would like to also talk about the preliminary experiment done for 1D atoms in a 1D lattice instead of the 2D, instead of the dimerized lattice. And this is a preliminary result, but we could observe the ferromagnetic spin correlation, which indicates formation of the decay state. And we plan to repeat this measurement for various lattice geometry to reveal the novel property of this dissipative Fermi-Hubbard model. Okay, and maybe final topic is about quantum magnetism in a Plaquette lattice. Here we load SU6 Fermi gas into isolated Plaquette lattice like this. Okay, and interestingly, the ground state of the four spin state loaded in a Plaquette lattice is SU4 singlet state, which is described like this. And here the IJKL represent site index, and 1, 2, 3, 4 represent spin index. And this SU4 singlet is the 4-spin entangled state, and it is a natural extension of the 2-spin entangled state of a spin singlet state or a Bell state. And this SU4 singlet state can be expressed also like this as a direct product of the SU2 type spin singlet state for vertical and horizontal direction. So we expect a perfect antiferromagnetic spin correlation for any pairs within the Plaquette. And this is different from the case of SU2 in a Plaquette. And the ground state is S wave RVB state, written like this. And in this case, the singlet fraction is below 1. Okay, and this is a result of the measurement of the spin correlation for the case of SU6 loaded into Plaquette lattice, and as a function of the anisotropy of the hopping between the horizontal ring and the vertical ring. And so here correspond to the case of Plaquette lattice, and here correspond to the case of a dimerized lattice. And importantly, we obtained almost perfect spin correlation for both direction, both horizontal and vertical rings for in the case of the Plaquette lattice. And this is different from the case of the SU2. Here, even in the Plaquette lattice configuration, the spin correlation is much below 1. Okay. So in this way, we could successfully form the SU4 singlet state confirmed by the measurement of spin correlation. Okay, and this is a summary of my talk, and I will not repeat this, but as a prospect, we want to observe the long-range spin correlation of SU and fermions. This is possible by developing the quantum gas microscope for ytterbium 173, which is underway in our lab. And finally, I would like to introduce our group members. These people are working very hard for the experiment in this talk, and especially Dr. Taie made a great contribution for the experiment in this talk. And as I mentioned, we have recently have a nice collaboration with SUN theory team of Caden Hazard and Richard Scarletta and Eduardo Ibarra Garcia Padilla and Hao Tian Wei. Thank you very much for your attention.
Thank you very much, Yoshiro, for the really nice talk and the fascinating new results. It's amazing to see the really broad range of new things going on in your lab, and really very exciting. So thank you very much again for that. We have a few questions. So the first one is from Jonathan Hirschele, and he asks, except for even higher singlet-triplet imbalance at STO amplitude, what would you expect if you perform experiments with SUN systems with n greater than 6? So how would you expect these things to change for n greater than 6?
For example, strontium, it's 10 spin degrees of freedom. So I think that we should be careful about the STO signal. Yeah. So we created the spin-dependent potential gradient by optical means with the off-resonant laser beam. And so with 6-spin component, we have 3 STO frequency. So if you work with, for example, a 10-spin component, you may have more STO frequency. So the STO signal becomes more complicated. So if you have a good signal to noise ratio, then it doesn't matter. But yeah, you should be careful about that. Yeah, so that is one point I can say.
Okay. We have another question about the comparison of these sort of spin correlations in the 1D systems versus in the 3D systems. So you have this really beautiful comparison with the experimental results and the theoretical results. In the regime where it was possible to do the theory calculations, for the 3D and the 1D theory calculations, sort of at these higher entropy values, it seems that the 3D and 1D results from theory are very similar, whereas already in that regime in the experiments, you seem to see much lower correlations in the 3D system compared with the 1D system. Do you know where that discrepancy might come from? Things that are not being captured in the theory, or do you know maybe how to explain that discrepancy?
Sorry, discrepancy between
so around sort of the S over N KB is sort of 2.5 or so. The theoretical results, the green line and the red line are very close, whereas the experimental results are very different to each other. Do you know maybe what's not been captured by the theory there?
Right now, we don't understand this discrepancy. And yeah, the one reason is that our experimental data has some uncertainty. It has some fluctuation. So yeah, that might be a possible reason. But also, we have some heating mechanism in our optical lattice loading process. So some heating might explain the observed discrepancy. But yeah, it also depends. Discrepancy is different for singlet-triplet imbalance and STO amplitude. So yeah.
Okay. No, I mean, they're very, very interesting results, and the sort of fascinating also to understand some of those elements. So the next question is on the dissipative Hubbard model with SU6. So these are, again, really interesting new results. Do you find, so you found this sort of transition from an antiferromagnet to a ferromagnet. In some of the theoretical papers looking at this for the SU2 case, was found that if you leave the dissipation on, that you would expect to go into some sort of non-zero steady state atom number when all the symmetries are such that you don't get any more loss in the dissipative model. So do you find that you can do that, at least to some extent, to leave the loss on and settle into a steady state atom number, or does that not happen in the SU6 case?
I think that the Klaus-Zenkstock group already observed such a steady state atom behavior for SU6. They introduced the intrinsic two-body dissipation in the case of P0, inner collision between the P0 atoms. Yeah, but their case corresponds to the SU6. Also, they worked with SU2 also. But in our case, we can study, we can reproduce this behavior for SU6. Yeah.
That's really very, very nice. So a couple of sort of broader questions to finish up. So what do you see as the perspectives maybe for reaching even lower temperatures in these SUN systems sort of over the coming years? What do you think is possible, and what do you expect to see? Could you see something like, superfluid pairing and things like that in these systems, or what would be your expectations for the coming years?
Yeah, it depends on the development of the quantum gas microscope for ytterbium 173. So if we could develop a nice quantum gas microscope, then we can employ the spatial entropy redistribution technique and so on. So yeah, but the machine is still under construction. So, but yes, another point is that as I said, we can introduce the spin imbalance. Then we don't know the how well the Pomeranchuk cooling works in such a spin imbalance case. So if it, I think there is a possibility that Pomeranchuk cooling works very well for such spin imbalance case, and also we can work with the another filling. Yeah. So right now we are mostly working with the 1/n filling, but we can work with a much higher filling. Then Pomeranchuk cooling works even better for such system. Then we can get a lower temperature for such system. Yeah. So, but just speculation. Sorry.
Okay, and finally, one broader question. So you've done a lot of work pioneering the use of ytterbium in these sorts of experiments. If you look at the sort of the possibilities, maybe over a longer time scale, take sort of the next sort of 10 years in the development of these sorts of systems and other applications of these two-valence electron atoms, what excites you most about, be it potential connections to many-body physics or other applications of these things? What do you see on the horizon that excites you most in these systems?
Yes, the two-electron atoms are now used for various physical research, such as quantum computation using for Rydberg atoms. Yeah, and also it has a ultra narrow optical transition. So this is very important for the study of the fundamental physics. Yeah. So yeah, optical lattice clock works very well for ytterbium atom. So if we combine the benefit of the quantum many-body system of the quantum gas and precision ability of the precision measurement, then I think we can explore some interesting new physics.
That's great. Well, thank you very much, Yoshiro, again, for the really nice talk and the wonderful new results that you presented from your lab. And I'll hand back to Sebastian for the final closing words.
Yeah, thank you very much.
Thank you also from my side, Yoshiro, and I can only agree with your last statement that combining quantum many-body physics and precision measurements is a great idea. And with that, I'd like to announce that next week on April 1st, no April joke, we have another talk by Monika Schleier-Smith, who will talk about quantum spin dynamics. And you should certainly check out our sister seminar, the virtual AMO seminar, where tomorrow they'll have Giulia Zemeghini speaking about topological spin liquids. We would also like to remind you of our next hot topics session, the deadline for which is next week on Friday, April 2nd. So please send us your nominations if you haven't done so. And with that, if you want to know more about what we do, please go to our website, quantumscienceseminar.com. You can subscribe to our email list there and our Google Calendar. You can even follow us on Twitter now. And with that, I'd like to thank you for your interest, and we hope to see you again next week, same time, same place. Bye.